Swayam Prabha. Digital India. Educated India.
Hello friends, welcome back to the fourth module of our MOOCs course on the topic of fundamentals of nuclear power generation, and today we are going to continue our discussion on the topic of chain reactions in reactors. You were introduced to this topic of chain reaction during the previous lecture, and if we quickly revisit the content of the previous lecture, the importance of chain reaction were emphasized there. It is just one fission will not give you any kind of realistic power production. Rather, the neutrons which are produced from the fission reaction must induce fission to some neighboring nucleus as well, and then only we shall be able to sustain a continuous power production procedure, and that chain reaction therefore is extremely essential. However, it is as we have already seen, it is not as straightforward that just the neutrons coming out or getting produced from a fission reaction, all of them will be able to produce fission, a subsequent fission. Rather, they will go through several kinds of phenomenon, and accordingly there is very less chance that a neutron can cause a fission. In fact, that is just one of the several possibilities. So, to characterize that, we have you are introduced to the topic of multiplication factor and reactivity. Multiplication factor basically gives you the idea about the number of neutrons that are produced per unit neutrons absorbed in a reactor, and reactivity is defined by this relation, which is multiplication factor minus 1 divided by multiplication factor or effective multiplication factor. There are several factors on which this multiplication factor depends on. To understand that, we discussed about the neutron life cycle, like this picture was used for that. A freshly produced or introduced first neutron goes through several stages inside a nuclear reactor, like first is goes through first fission, which we can characterize using the first fission factor. Then it can undergo through a first neutron leakage. So, corresponding non-leakage probability can be identified with something like this. Then it goes through the moderation process, during which the first fission or rather first neutron gets converted to thermal neutron level, but several elements present inside a reactor, particularly uranium 238 has very high resonance absorption capability, that is the absorption peaks are extremely high in the resonance capture zone. Accordingly, some of the neutrons may get lost in the form of resonance absorption, and corresponding escape probability was identified or characterized in terms of small p. The newly produced thermal neutrons, then some of them can get leaked outside, which we shall be discussing very shortly, this leakage procedure or movement of neutrons, but corresponding non-leakage probability was identified as Pt or Pta sometimes to make it thermal. Then neutron will get absorbed, these thermal neutrons whatever remains, whatever survives the leakage, they will get absorbed in the reactor. But there are not only fuel, but there can be several other elements also which are absorbing these thermal neutrons, like the moderator, the coolant itself, and several other elements which can be there, like the control elements, etc. So, our interest is to identify how much fraction of whatever getting absorbed is actually getting absorbed by the fuel. That was characterized by a thermal utilization factor small f, and then whatever factor that gets whatever fraction that gets absorbed by the fuel, that goes through or induces the thermal fission procedure. So, all of them again may not induce a thermal fission, because some of them may go through a non-fission capture process in the fuel itself, and finally, whatever we get back, that is characterized in terms of a thermal fission factor eta. So, all these 6 factors were introduced. Out of these, 2 of them are leakage characteristics, this Pf and Pt, and therefore, they depends upon the configuration of the reactor, but others They also depends upon the configuration reactor plus fuel plus whatever other assemblies are there inside, etc. So, this particular very popular and very important relation was introduced, where k infinity on the left hand side represents the infinite multiplication factor. It is basically the multiplication factor for an infinite reactor, that means when there is no leakage. So, corresponding multiplication factor is given as the product of these 4 factors. So, that is why it is also called a 4 factor formula. Then we have discussed about the process of calculating all these 4 factors, and in between the role of reflectors are also mentioned to reduce or capture the leakage and reflect the neutrons back to the reactor. So, to start with, today we shall be first seeing one numerical example to see how we can calculate all these 4 factors in a real reactor situation, and also how can we use them to calculate the reactivity. So, this is the example problem that I have selected. Please read the problem carefully. Here the problem is to calculate the infinite multiplication factor and also reactivity for a reactor where we have a solution of uranyl sulfate. Now, remember, uranium is of course the fuel. Uranium 235 particularly is the fissile isotope which you would like to use for fission reaction, but uranium is also quite active chemical point of view, and therefore, the uranium that we introduce in the reactor, that is not pure uranium, that is rather more in form of some kind of compound like some oxides or carbonates, something like that. And here this problem uses a sulphate which is uranyl sulphate UO2SO4, and it is also immersed in heavy water. Heavy water, I have mentioned earlier, refers to the water where the hydrogen actually is deuterium, that is deuterium isotope. So, here you are having uranyl sulphate as one element. Inside uranyl sulphate molecule you have uranium isotopes or uranium nucleus, which is actually your fuel, and also you have heavy water. Heavy water is a very strong moderator. So, that will act as the moderator. The composition is also given. For every molecule of uranyl sulphate we have 1000 molecules of heavy water, and the fuel uranium can have different kinds of isotopes actually. So, here the fuel contains natural uranium, that is out of all the uranium isotopes present only 0.715% is uranium 235, rest are uranium 238. So, we have to calculate the multiplication factor, the infinite multiplication factor. So, let us just revisit the mathematical relations that we have derived during last lecture. This is the thermal fission factor. Of course, it is defined as a ratio with in the numerator having the macroscopic fission cross section of the fuel. You have to remember there are several elements associated in this particular problem. Like, what are the elements? How many elements you can identify? One is the uranium, then second is oxygen, third is sulfur, and fourth is this heavy water. There is no need of separating D and O here, we can treat them as the same element or just a single element. But so we have 1, 2, 3 and 4, but is it correct? Probably something we are still missing, because uranium is not a single element, rather we can have two kinds of isotopes of uranium. One is uranium 235 and other is uranium 238. So, basically there are 5 different kinds of elements or isotopes that are involved in this particular problem. So, we need to know the characteristics of all these 5, but out of the 5 only one has fission cross section at the corresponding to whatever neutron level that we are dealing with. This problem actually concerns thermal neutrons. So, corresponding to thermal neutrons only uranium 235 is the one that is having fission cross section. So, to calculate the fission thermal fission factor, in the numerator we need to use the macroscopic fission cross section of uranium 235 multiplied by, here nu is the average number of neutrons produced for fission for this uranium 235, divided by the total absorption cross section of the fuel. Now, here fuel refers to both uranium 235 and uranium 238. So, while calculating the denominator, we have to consider the absorption cross section for both these two isotopes 235 and 238. However, while calculating the numerator, it has to be only uranium 235, because uranium 238 does not have any kind of fission cross section for thermal neutrons. Next is the thermal utilization factor. Now, in the numerator we have the total absorption cross section of the fuel. Basically, the denominator which we have used here, the same denominator is coming to this as the numerator, but what we have as the denominator for this thermal utilization factor, here the total absorption cross section for all elements that can be present. So, here we have the fuel absorption cross section for the fuel, or absorption macroscopic absorption cross section for the fuel, same as the numerator. We have the absorption cross section for the moderator, which is the D2O. Here this control rod, this boron, this poison, all can be eliminated as no information are given about them. But we have also this other. Now, what comprises the other in this problem? It is the oxygen and the sulfur which are also present in this actual problem. Next is the resonance absorption cross section. This mathematical relation was given, which is based upon an empirical formula. Here this sigma s in the numerator refers to the total scattering cross section of all the elements present inside the reactor, and zeta bar is the weighted average logarithmic energy decrement for all the elements. Again, we have seen how to calculate these two factors. Finally, is the first fission factor. Now, what should be the value of first fission factor? It was mentioned earlier that when the moderator nuclei by fuel nuclei, that ratio is more than 50, we can neglect any kind of first fission and can take this first fission factor to be equal to 1. Here this ratio is 1000, because for every fuel isotopes or fuel molecule we have 1000 molecules of D2O. So, we can take this first fission factor to be equal to 1. Now, we need to have several properties, that is all these cross section values that we need to know this. So, these are the property informations that are given to us. Atomic weight for all these elements are given, scattering cross section is given. For here both U235 and 238 are having the same scattering cross section. For the others they are given, D2O definitely have a much higher scattering cross section. Sigma c, that is the capture or non-fission absorption cross sections are given. Uranium 235 has a quite high, but very interesting that oxygen is value is 0 for oxygen, and for D2O it is also extremely small, almost negligible. So, deuterium is an excellent moderator, whereas the scattering cross section is quite high, its absorption cross section is negligible. Then we have the fission cross section. Of course, all these elements are non-fissionable for thermal neutrons. So, only uranium 235 is having the fission cross section, and correspondingly the average number of neutrons produced per fission is given for the same element. So, with these property values, now we have to solve this problem. That is, we have to basically calculate the values of all these 4 factors, because as we have derived in the last class, K infinity is equal to the product of this all 4 factors: the thermal fission factor, thermal utilization factor, resonance escape probability, and the first fission factor. So, we have to calculate all these 4 factors, and accordingly we shall be able to calculate this K infinity. And also, if our interest is to know the reactivity rho, that is in this case K infinity minus 1 by K infinity. Of course, the actual definition of reactivity uses in effective multiplication factor, but as no information is given about the leakage characteristics. So, we can take K effective to be equal to K infinity, or we can consider this problem to relate to some kind of infinite reactor. Now, another relation that we need to use, that is the zeta. This relation we have derived as a part of our third module. Once we know the atomic weight for any isotope, we can calculate, or mass number for any isotope, we can calculate the zeta for this. So, now we expand the table. Here the same table from the previous slide I have taken, those written in black were the information given to us, but those in blue that we have newly calculated. I have calculated this for you, and I have filled up the table, but let us explain one by one. First is N. N refers to the number of isotopes for that particular element or particular compound present for every molecule of the fuel. So, for every molecule of the fuel, we know our fuel is UO2SO4, or we have UO2SO4 and D2O. So, for every molecule of UO2SO4, we have how many molecules of sulfur? Just 1, and for oxygen, that is 2 plus 4, that is 6, and it is also given for every molecules of UO2SO4, we have 1000 molecules of heavy water. So, that is 1000. But every molecule of oxygen also, every molecule of uranium also contains just 0.715% of uranium 235 and rest uranium 238. So, uranium 235 corresponding N is 0.00715 and for U 238 is 0.99285. Then sigma S is given. So, we compute N into sigma S, just multiply all the sigma S values with corresponding N and then take their summation, or if I write properly, this is the summation for N sigma S. Just same way we get N sigma C, that is the here N sigma S represents what? This represents the macroscopic scattering cross section for every element, and this is the total summation. Now, this represents the macroscopic capture or non-fission absorption cross section, and this one N sigma F is the macroscopic fission cross section. So, we have calculated using the microscopic cross section values and value of N, we have calculated the macroscopic cross sections for scattering, capture and fission. Next is zeta. The relation is already given. For this, the value of zeta we can compute for all these elements. Apart from D2O, the value of zeta for D2O actually is given in the problem statement, because this particular relation here A refers to the atom mass number of any isotope, and hence we can calculate it only for a single element, but not for a compound like heavy water. So, this value of 0.509, that has to be given in the problem. Here we can assume it to be given. And once we have evaluated the zeta value for all the elements, we calculate N sigma S into zeta for all of them, and again we take a summation of that. So, once we have all of them, now you have to calculate the 4 factors. First is the eta, the thermal fission factor. So, how to calculate thermal fission factor? We know it is a ratio. In the numerator, what we have? Average number of neutrons produced for fission. Now, it was given in the previous slide. It is 2.42 for uranium 235 multiplied by total macroscopic fission cross section for that fuel, which is this particular thing. So, that will come here. In the denominator, what we have? It should be the macroscopic absorption cross section for the fuel. Now, fuel refers to uranium 235 and 238 together. So, in the denominator we shall be having the total non-fission capture cross section for these 2 elements, that is this plus this particular one, the absorption cross section. So, once we put all this back, or if we write carefully now in the numerator, then we are going to have again 4.13985. In the denominator corresponding to the fission part 4.13985 plus 0.72215 plus 2.700552. So, once we put all these numbers, then corresponding value of eta comes out to be 1.3247. We have to calculate thermal fission factor. Let us just erase this clutter from here. So, to calculate the thermal fission factor now, we have to take the ratio. Again in the numerator, what we are going to have, that is going to be the macroscopic absorption cross section for the fuel, that is macroscopic absorption cross section for the fuel refers to the denominator that we have actually used for eta, that is this 2 plus this is the numerator. And what about the denominator? Denominator refers to the total absorption cross section for all elements involved. So, denominator is this quantity plus this one. So, and once we put it back, then we get F equal to 0.8326. So, we have now 2 quantities N and eta and F. Now, we come to the complicated one, that is the resonance escape probability. Now, to calculate resonance escape probability, first we need to know the weighted average value of zeta. So, zeta weighted average value, that was given earlier as summation of n sigma s zeta for all elements divided by summation of n sigma s. where this denominator actually is the total scattering cross section, which is this quantity, and a numerator this one that we have already evaluated. So, if we get the ratio, it comes to be 0.5077. Now, mathematical relation for P was given earlier. So, which is exponential of minus 2.73 by zeta bar into sigma s by n number of U-238 isotopes whole to the power minus 0.514. So, if we put it back, then we are going to get P equal to 0.9554. So, and epsilon already we know it is equal to 1. So, we combine all of them, and finally, the value of effective multiplication factor is coming to be 1.0538. Then what should be the reactivity? Reactivity is 0.0511, that is, it is a what kind of reactor this is, critical, subcritical or supercritical. When K effective is equal to 1, that is a critical reactor, when it is less than 1, that is subcritical, but in this case it is a supercritical reactor because reactivity is positive and K effective greater than 1. That means, the rate of reaction will keep on increasing with time, and we shall be having a diverging chain reaction. So, this way we can calculate the values for the multiplication factor and reactivity for any kind of situation. I would request you to try different variations of this problem, like if you here this problem concerns natural uranium, you can try the same for enriched uranium. Let us say the fuel contains 5% uranium-235 and rest uranium-238 and see how it varies. And also you can try to see the effect of that such enrichment on this eta. This is natural uranium, which has 0.7% uranium-235 and corresponding value of eta is 1.32. Please try to calculate the value of eta for different enrichment factor. As I have shown in a graph, you will find that beyond 10% it becomes almost saturated and the corresponding value is around 2.06. Correspondingly, you can try to calculate the reactivity values for different enrichment factor, and also by taking other kind of substance, like instead of D2O, if you are taking normal water H2O, which has a slightly lower scattering cross section and much more significant absorption cross section, non-fission absorption, that is. So, correspondingly what value you are getting, you can try to do the calculation, but procedure always remains the same. When whatever data are given to you, you always try to compute the macroscopic values and take their summations, like the macroscopic scattering cross section its summation, the capture cross section, fission cross section. Generally there will be only a single element for fission, but you may encounter problem where you have both uranium-235 and plutonium-239. Then not one, but there will be two fissile isotopes, and so the fission cross section will be having contributions from both. You also need to compute this summation of n sigma is zeta, and of course, you need to compute the values of all these zetas. Using this, we can finally compute all the values of effective multiplication factor and the reactivity. Now, this is a problem that was evaluated as neglecting any variation in the neutron flux. That is, while we evaluated the expressions for this F suppose or say eta, we have considered, say let us take the example for eta. While writing this, we have neglected any kind of effect of the beam intensity of neutron. That is, we have assumed the beam intensity of neutron that is incident on uranium-235 and uranium-238 part are identical. And much more strikingly, for calculating this thermal utilization factor, we have considered this intensity to be equal for all elements like moderator, coolant, etc. But practical reactors may not be having that scenario, rather neutron flux can vary significantly over a reactor, even in case of a homogeneous reactor. So, let us discuss about neutron flux and corresponding interaction. If we just if you can just go back to the second module that we discussed, there we have defined the reaction rate to be proportional to several components, and accordingly we have found the reaction rate was to be equal to sigma into the neutron beam intensity into the number of neutrons into volume, if say R represents the reaction rate. And if our interest is to know the reaction rate per unit volume, then it was something like this. Correspondingly, it was also mentioned, it was I into capital sigma, because nuclei density and microscopic cross section, their product is the macroscopic cross section. Here this I refers to the intensity of neutron beam, but as we are talking about the variation of neutron flux inside this reactor, instead of I quite often another symbol is used, which we shall be seeing shortly. But the issue is that while writing that simplistic expression, the variation in the beam intensity was neglected, but let us try to get a more involved expression now. Let us assume a monochromatic beam of neutron. Monochromatic refers to all the neutrons are having more or less the same energy, or the energy of the neutrons are confined within a very narrow band, so that they can be viewed to be almost a single energy. Then in correspondingly in E refers to the neutron density per unit energy, and in NEDE this product then represents the total number of neutrons per unit volume which are having energy within the small band of E to E plus dE. So, NEDE represents the neutron density at this particular energy level. Sigma T E is the macroscopic total cross section at that energy level, because you have to remember that cross section varies with energy. So, it will also it is also dependent on the energy, and finally, the velocity of this neutron, velocity being directly related to kinetic energy. So, it is also going to vary with the energy level. Then once we have specified one energy level E, or maybe we have considered a very small energy band across this E of thickness dE, then the total number of interactions that we are expecting to have per unit volume is given by this expression, or this N into V can be combined into something called neutron flux per unit energy. This is actually identical to that symbol I that we are using earlier, but generally phi is a more common symbol, and I is more used to characterize the intensity of neutron beam that is incident on some kind of surface, like we have an artificial source of neutron and we are producing neutron there, that neutrons are striking some targets. But here we are talking about the movement of neutron inside a medium. So, it is more convenient to use the classical symbol phi. So, phi E refers to the neutron flux at that particular energy level, but neutron energy varies strongly with or the fraction of the neutron which are appearing at a certain energy level very strongly with the energy. Like you can see from this diagram, at this particular energy band the neutron density is quite high, whereas at level somewhere here the neutron density is quite low. So, with the energy level both neutron density and accordingly the cross section and velocity also varies, and hence to get an idea about the total cross section that is happening over this entire band starting from this 0 energy level to some extremely high energy level up to infinite, then we need to integrate this equation from 0 to infinity, and this is what is the total rate of interaction per unit volume we are going to have. So, here this sigma T refers to the total macroscopic cross section corresponding to a particular energy level. Similarly, this phi is also the neutron flux at a particular energy level, and both are strong functions of energy, neutron energy that is, and if we know their nature, then we can of course evaluate this integral. Quite often instead of calculating the total interactions, our interest is to know about any particular interaction. Like say if we are dealing with a moderator, our primary interest is to know how many collisions will be required for a fast neutron to slow down to the thermal neutron level, and hence our major interest is to know the rate of scattering collisions or scattering interactions. So, we can just replace this subscript of this, replace the subscript of this total cross section and use the corresponding subscript, and we can get the corresponding rate of interaction. Like for scattering, we need to consider the scattering cross section. Similarly, if our interest is to know the absorption, total absorption, that is, we need to consider the absorption cross section. And quite often nowadays with the advent of computers, we always like to go for digital techniques. So, instead of going for a continuous integration, like if we want to evaluate this particular integral, we need to know the energy relation, or we need to know how sigma A and phi both are depending on energy. But quite often numerical approaches are used. Numerical approach refers to this total domain of energy starting from here to this is being divided into several small elements. Like we take several small elements each of some constant or varying thickness. So, this is the thickness of one element, and to know the value of this interaction at that, we can always multiply the thickness of the element with the cross section at that location and phi at that location, and then we can sum that product up for all such elements present in the domain to get the total rate of interaction. So, once we know the rate of interaction, then we need to define something called the mean free path. But now, rate of interaction, whenever there is an interaction, of course, a neutron goes out of the package, and therefore, there will be a change in the neutron flux as well. We can equate these two factors to get some kind of balance, that is, rate of interaction should be equal to the rate of change in the neutron flux multiplied by the cross section area. Let us consider some elemental area, something like this. This area is A, this area is A, and this thickness is dx. Then the rate of interaction as per our classical relation is sigma t into phi n a dx, where sigma t again is the total cross section, phi is the corresponding neutron flux across which is going through this area, n is the nuclei density, and a dx refers to the volume. That should be equal to the rate of change in the neutron flux into the area. Here this minus sign is used to indicate that as we are moving forward in the x direction, the neutron flux is reducing. So, if we rearrange, we are going to get this, and finally, we arrive at this, integrating it from x equal to 0 to, means we are integrating this equation from some x equal to 0 to some x. So, phi at x equal to 0 is referred to as phi 0, and correspondingly we get an exponential relationship, that is, this neutron flux in such a geometry will follow an exponential relationship. This is called a survival equation, because this characterizes the rate at which neutrons are survived while flowing through such a medium. And here sigma t we are using, so it considers all possible interactions that can be there. And there is often something called thin target approximation that we take, like thin target approximation refers to we use the earlier approach. That means, we neglect any variation in the neutron flux, rather we assume the neutron flux to be constant over the entire domain of our interest. If we generally that kind of approach can be used when the variation in this phi is less than 1% of its initial level. So, we can use this thin target approximation when this phi x at any location, basically we are talking about the x equal to L, the end of the target. At this location, the value of phi is within 99% of the initial value. And so, if we rearrange the term, that gives a criteria of this sigma t into L should be less than 0.01. That is, when this criterion is satisfied, we can go for this thin target approximation. That means, we can neglect any kind of variation in the value of phi, and we can assume it to be constant everywhere in our target nuclei. Now, mean free path is defined as the average distance travelled by neutron without any kind of interaction. That is, once a neutron enters a medium, of course, different neutrons will interact differently with the neighboring molecules or neighboring nuclei, and accordingly the travel distance will be different for different neutrons. But mean free path defines the average distance travelled by a neutron without any such kind of interaction, and hence this is defined as lambda is the symbol that we commonly use, and using the symbol lambda we can define it as 1 by phi naught into integration x equal to 0 to infinity x d phi. If we put the expression for phi that like this particular survival equation, then we can simplify it to this, and finally lambda coming to be the reciprocal of sigma t. That is, the mean free path is found to be reciprocal of the total macroscopic cross section. Instead of going for the total approach or all kind of interaction, we can make it specific to all any particular interaction as well. Accordingly, we can define a lambda s, that is scattering mean free path, lambda a absorption mean free path, and even a fission mean free path as well. All of them will be reciprocal to the corresponding macroscopic cross section. Like if our interest is to know the lambda a, that is absorption mean free path, that is the average distance travelled by neutron before it will get absorbed in the medium, that will be one reciprocal to absorption cross section, macroscopic absorption cross section. Now, when the value of this absorption cross section is extremely high, or I should say when the value of this absorption cross section is extremely high, the value of this mean free path corresponding lambda A is definitely much lower, and accordingly most of the neutrons may get absorbed in the surface only before going into the interior of the medium. But this concept of mean free path is a very important one, and once we have the data available about the cross section, we can calculate all kinds of mean free path. But there is another mean free path which is often defined, that is called the transport mean free path. Transport mean free path refers to the average distance travelled by neutron in its original direction after infinite number of scattering collisions. Let us look at this diagram. Say this is the point from where the neutron is entering the medium. So, before it encounters any kind of scattering interaction, it is likely to travel lambda s distance, lambda s being the scattering mean free path. So, here it will be encountering on an average, this is the location where it will be encountering the first scattering location, scattering interaction, and hence it will get scattered by some angle. Then if this angle is psi, then it will encounter again following this particular line, it is likely to travel lambda s amount of distance, and hence after it has travelled lambda s into mu bar distance, it will encounter another scattering collision here, and this will keep on continuing. Here this psi bar refers to the average rate of angle of scattering for the neutron. Of course, different scattering may lead to different angle of deflection, and psi bar is the average of that, and this mu bar is the cosine of that psi bar. So, while the neutron will first experience any kind of scattering after travelling this lambda s distance, it will be able to travel only lambda s into mu bar before in this original direction of motion. It is important to note that we are doing everything in terms of the initial direction of motion. So, lambda s mu bar will be the distance it will travel before the second scattering collision, and mu bar square before the third one, and this way it will continue till infinity. And this mu bar, something that is beyond us, but statistically it can prove that mu bar is actually 2 by 3 into A, 3 into A, where A is the mass number of the target nucleus, which is or the moderator nucleus, which is inducing the scattering. So, if we want to know the value of this transport mean free path, TRs always transport, we need to sum up all these distances, that is lambda s for the first one, then lambda s into mu bar for the second one, lambda s into mu bar square for the third one till infinity, and mu bar being a cosine function. So, it is always less than 1. So, this infinite series can be combined into lambda s into 1 upon mu bar, or lambda s being the reciprocal of sigma s, that is macroscopic scattering cross section. We can write this particular thing, that transport mean free path is equal to the reciprocal of means scattering macroscopic scattering cross section into 1 minus mu bar. So, while you need to know the value of this macroscopic cross section, that is microscopic scattering cross section and molecular density, nuclei density, that is, we also need to have an idea about average angle at which this scattering is happening, that is the psi bar. Of course, this formula is valid neglecting any kind of absorption in the medium, that is, we are considering the neutron to go through only scattering cross section, but if neutron is present, this distance will be not the same, rather this distance will be slightly lesser depending upon the value of other cross sections. So, with when significant absorption is present, this is another relation that can be derived, where lambda transpose becomes equal lambda transport becomes equal to the reciprocal of total macroscopic cross section minus mu bar into scattering cross section, and we can do this calculation, we can found a relationship between the two as well. Next, we have the diffusion of neutron. This is related to the leakage of neutron that we are talking about. Leakage means neutron is not able to undergo any kind of interaction, rather whatever medium through which it is existing, it is travelling through the molecules of the medium and going from a place of higher concentration to a place of lower concentration, quite analogous to the movement of heat or diffusion of heat or diffusion of mass. Like the mass diffusion is often expressed in terms of the Fick's law, this diffusion phenomenon of neutron can also be expressed in terms of the Fick's law, which is this. Here this J refers to here phi of course is the neutron flux that we have mentioned earlier, and J is neutron current density in the x direction, which is given by this. It looks very similar to the phi, but there is one difference. Like the expression for phi is where it looks similar, but here this V is actually speed, that is a scalar quantity. Accordingly, neutron flux phi is also a scalar quantity, but the V here in the definition of current density is a vector quantity because it considers the direction of that velocity vector. You can think this about this way, like it is also possible when there is no net motion of the medium, still significant amount of interaction is taking place. That means the total speed of the medium is 0, but there may be individual components which are participating in interactions, and hence they are interacting or oriented such that their net is coming to be equal to 0. So, neutron current density is a vector and phi neutron flux is a scalar. If we are talking about an unidirectional flow, then they have to be identical, this both in terms of magnitude and direction. Phi does not have a direction, but still the magnitude point of view J and phi will be equal only for unidirectional flow. D is the diffusion coefficient here, so which can often be related to the 1/3 into the transport mean path. Now, what should be the unit of this diffusion coefficient? Can you tell from this Fick's law expression? Here phi is the neutron flux, that is, so what should be the unit for phi? It is the number of neutrons divided by the area through which it is flowing through. So, it is meter square and per unit time, and it is also same for J. In case of J, only one thing here, it is this being a vector, Jx basically refers to an area which is having its perpendicular in the x direction, and J refers to the neutron current density which is flowing in that same direction or perpendicular to the area. Yes. So, the unit for phi and J are equal, and hence what should the unit for D? The unit for D should be, or dimension should be, that of length, like its SI unit should be meter then. So, diffusion coefficient is something that characterizes the diffusion process of neutron through this, and diffusion coefficient we can calculate using the knowledge of the transport mean free path, and we can do the calculation of transport mean free path in terms of the scattering cross sections. This being a vector, we can always write all the 3 components for this neutron current density, and if we combine all of them, then we can write for a generalized 3D system, that is J to be equal to minus D into grad of phi. But Fick's law, before we apply Fick's law any further, Fick's law is very much an idealization, and there are several limitations for this, like it is limited only to the mediums, or it is where the absorption is extremely low. That is, when the absorption is significant, absorption of neutrons, then we should not use Fick's law. Similarly, we have neglected the presence of any kind of source. Therefore, when the neutron is or the location that we are analyzing is very close to some kind of source or sink, as a rough guideline, about 3 mean distance away from the source or sink or from the surface of a medium, we should not use this. The neutron scattering, if it is strongly anisotropic, then also we can't use it, because in the neutron intensity will keep on varying in different directions. If the medium is non-uniform, then the value of the diffusion coefficient and other scattering cross sections etc., that will keep on changing with the location. So, we should not use the Fick's law. And finally, when the neutron flux becomes time dependent, this is very much a steady state equation. So, if the neutron flux is time dependent, we can't use this. Using this idea of Fick's law, let us write a neutron diffusion theory. Neutron diffusion theory governs the movement of neutron in a medium. So, rate of change of neutron, it is similar to any kind of say mass diffusion theory or mass diffusion equation or maybe energy diffusion equation. Thus, the same way you can write rate of change of neutron density should be equal to the production rate minus absorption rate minus leakage rate. rate of change of neutron density, we assume a small volume dV, infinitesimally small volume, then the rate of change of neutron within that volume can be given as dou n dou t of dV integrated over the volume. Production rate, S can be some kind of production rate, accordingly you get a simple expression. Production can be of from two possible sources. One is the fission reaction, other is if there is any external source of neutron. The absorption rate, in the absorption rate we can find the total absorption cross section multiplied with the phi integrated over the volume that we are dealing with. And finally, the leakage rate, it represents the grad of the current density, and J refers to the current density expression which we have derived, it can be related to the Fick's law of diffusion. So, we combine all these terms together here, and representing J in terms of the Fick's law, we arrive at this, because J is equal to minus d grad psi. So, we get this, here this grad square represents the Laplacian operator, that is the second derivative of phi, and this particular equation is called the one group diffusion equation. Also, we know that n is phi, the flux is equal to n into v, where v is just the speed. So, we can, considering the space and time dependence of relevant terms and using this relation of phi and n, we can express this one group diffusion equation completely in terms of phi, which is d into Laplacian of phi minus sigma a into phi plus s is equal to 1 upon v into dou phi dou t. These equations, derivation of this one is very much based on Fick's law, and so whatever limitations of Fick's law that we have mentioned in the previous slide, all of them are applicable here. So, there are situations like when there is a strongly absorbing medium or a non-uniform medium or a medium where there is anisotropic scattering is going on, there this is not applicable. Still, one group diffusion equation is quite simple and offers us a reasonable solution in several situations, particularly to get a rough idea about the design or as an optimal design of a reactor to attain the critical condition. If we restrict this analysis only to the thermal neutrons, then we are talking about this source term here. We are talking only about thermal neutrons, that is all neutrons present in the system are thermal neutrons, then the S can be really written as something like this, K infinity being the infinite multiplication factor into the first fission leakage probability. This is into sigma A into phi, sigma is the absorption cross section corresponding to thermal neutrons and phi is the neutron flux. So, these are the total number of neutrons which are available or which are getting absorbed during in the medium as the form of thermal neutrons. So, putting this back in the previous expression, we get this, and now we divide this entire equation with sigma A on both sides. Then here we are having one V into sigma A in the denominator, and the epsilon related terms they are combined into this, and we are writing L square as d upon sigma A, or d nearly being the 1 by 3 of into sigma s. So, this is L square. This L is called a diffusion length, a very important parameter in reactor design point of view. Importance of this one we shall be discussing in the next lecture. L square being similar, because of the similarity, is quite often called area. Like, what should be the unit of this L or L square? What is the unit of D? Unit of D is meter or length. So, SI unit of D is meter, as we have seen in the previous slide. What is the unit of macroscopic cross section? SI unit is meter inverse. Accordingly, unit for L square is meter square and L is meter. So, that is why we use the term L, we use L as length, or we define it as a diffusion length, and L square quite often called a diffusion area, as this dimension is of area. Now, we move forward with this, and we have divided this entire equation by L square now to get reduced to this form, and finally, we replace the two right hand terms with Bg square and Bm square. Here Bm square is equal to this particular quantity and Bg square is minus of this particular quantity. They are called buckling. Bm square is called material buckling, as it is a function of material composition only, and Bg square is called geometrical buckling because it is a function of geometry. Values of both these buckling parameters are very important while designing any reactor shape. If we consider steady state, if we want to attain a critical condition, that means K effective should be equal to 1 or reactivity should be equal to 0, and the rate of reaction should remain constant over a long period of time. Now, to ensure stable reaction, dou phi dou T is equal to 0. If we put it in the previous expression, that is here, then what we are going to get is Bg square is equal to Bm square is equal to say B square, which is called the buckling parameter. Considering Bm square equal to B square, we get K infinity to Pf by 1 plus L square B square is equal to 1. Accordingly, we can define an effective multiplication factor, effective thermal multiplication factor, as we can define an effective multiplication factor by separating out this K infinity and Pf from this expression, and whatever remaining we can call it Pth or just Pt, because I think earlier we have used the term Pth. So, neglect this earlier we have used Pt, so neglect this H here and let us continue with Pt only. So, here this Pth or Pt is a thermal neutron non-leakage probability and is 1 upon 1 plus L square plus B square. And if we take the second part of this particular equation, then we get Bg square is equal to B square, and rearranging Laplacian of phi plus B square phi equal to 0. This equation seems familiar. Have you seen it anywhere else? It looks very similar to the heat diffusion equation, and hence its solution procedure is also quite similar to that. But there are say boundary conditions, separate kind of boundary conditions which we must take into consideration while solving this. So, once we have a properly defined boundary condition, we can solve for this particular equation and get an idea about the nuclear reactor behavior or how to design a reactor. So, in the next lecture, we shall be trying to see or trying to subject this particular equation to different kind of situations and see the corresponding solutions, and we shall be defining the importance of this diffusion length probably. So, thanks for your attention today, and we shall be seeing in the next lecture.